Welcome to another tutorial on TwinCAT automation software from ControlX Engineering. Today we'll be continuing the topic of motion control in TwinCAT. This is a continuation of the motion control tutorial, so make sure to check out part 1 before watching this one. In part 1 of this tutorial, we explored the motion control node in Solution Explorer, added a simulation axis, and controlled the axis manually from the online tab. Today we'll learn how to control this axis from the PLC using PLCopen-compliant motion control library called TC2MC2. We'll look at the axis operational state diagram, and we'll review some of the most important access control function blocks. We'll create a new PLC project and implement the library to control the axis programmatically. Finally, we'll run this axis from the PLC using the motion control function blocks in various configurations using both position and velocity controllers. So let's get started. Let's go back to the axis dialog box and navigate to the settings tab. Last time we left the two link fields blank since we wanted to control the axis manually from the controls on the online page. If we click on the Link to PLC button, we get this dialog box asking to select the axis PLC reference. Once we create the PLC reference for all our axes, those referenced axes will all appear in this list, and we can choose the correct axis to link with the selected NC axis. The name of the link PLC axis reference will be shown in the text field here. In order to create the PLC axis reference, we will need to install the TC2MC2 library, which will provide us with the necessary axis interface containing the axis reference data type. The axis ref data type contains axis information and serves as an interface between the PLC and the NC. We can use the axis ref to instantiate as many axes in the PLC as required, and then link them to the corresponding axis in the NC. More detailed information about the TC2MC2 library can be found on Beckhoff's Infosys website. Use the information shown here to navigate to the library's documentation. The TC2MC2 library contains function blocks for programming motion-related machine applications. It is based on the PLCopen specification for motion control function blocks. PLCopen is a vendor and product-independent association for topics related to industrial control programming. The PLCopen motion standard provides a way to have standard application libraries that are reusable for multiple hardware platforms. PLCopen specifications contains definitions of state machines, which we will be reviewing next, and definitions of a basic set of motion control function blocks. We will explore the most important function blocks and use them in a PLC project to run our axis later. And finally, compliance rules and procedures for use of these function blocks are also defined. The state diagram defines the behavior of the axis at a high level when multiple motion control function blocks are simultaneously activated. This combination of motion profiles is useful in building a more complicated profile or to handle exceptions within a program. The basic rule is that motion commands are always taken sequentially, even if the PLC had the capability of real parallel processing. The axis is always in one of the defined states. Any motion command that causes a transition changes the state of the axis and modifies the way the current motion is computed. A change of state is reflected immediately when issuing the corresponding motion command. Arrows used in the state diagram show the possible state transitions between these states. State transition due to an issued command are shown by the solid arrows, while the dashed arrows are used for state transitions that occur when a command of an axis has terminated. The motion commands which transit the axis to the corresponding motion state are listed above these states. The disabled state is the initial state of the axis. In this state, the movement of the axis is inhibited and therefore not influenced by any of the function blocks. To enable the axis, it requires the MC power function blocks, which will transition the axis to the standstill state. When the axis faults, it switches to the error stop mode and stays here until the fault condition is cleared and the axis has been reset using the MC reset function block and brought back to the standstill state. From standstill, the axis can be transitioned to either of the motion states using appropriate function blocks. For example, we can use the move absolute positioning function block to move the axis to a desired position, after which it switches back to standstill and is ready for the next command execution. All function blocks that can affect the state are shown on the diagram. Function blocks which are not listed on the state diagram do not affect the state, meaning that whenever they are called, the state does not change. One example of such a function block is MC read status. The axis ref data type contains NC information about the axis. Axis ref provides an interface between the PLC and the NC to cyclically exchange notification and control data between the two. Using the NC to PLC data structure, the motion control function blocks in the PLC communicate with the NC to receive notification or status information. This data structure is automatically placed in the input process image of the PLC. The NC to PLC structure contains all the main state data for an axis. such as position, velocity, and instruction state. Since data exchange takes place cyclically, the PLC can access the current access state at any time without any additional communication effort. Using the PLC to NC data structure, the MC function blocks communicate with the NC and send control information from the PLC to the NC. This data structure is automatically placed in the output process image of the PLC. To instantiate an access in the PLC, it is as simple as declaring an access variable of type accessRef. This can be done either locally in the declaration section of a POU or in a global variable list, as I have done here. Once declared, the NC to PLC and PLC to NC components of the access appear under the PLC instance as inputs and outputs. After that, the access can be linked to the PLC. Once linked, notice the overlay arrows indicating that the NC to PLC and PLC to NC are linked between the NC and the PLC. After the configuration has been activated, we should now be able to control the access from the PLC as well as read all the access status information. Next, let's review the library structure. The TC2-MC2 library contains data types and function blocks. Let's take a look at some of the common components of this library. Under data types, we have the access reference data structure, which we saw earlier includes the access IO variables as well as additional information. The function blocks are defined in the POUs folder and classified based on functionality. For example, as shown are the access functions, which include function blocks for enabling, resetting the access, as well as setting a position. Under status and parameter, we have function blocks to read crucial information like actual position, velocity, access errors, etc. The point-to-point motion folder contains function blocks for executing motion commands like move absolute, move relative, move velocity, as well as halt and stop functions. Let's review some of the important function blocks next. The MC power function block is used to enable the power stage of the linked access by controlling the software enable of the access. Enable can be activated either for one direction of travel or for both directions by using the positive and negative enable inputs. Now, one thing to note is that almost all function blocks that we are going to be reviewing here today will have an access input and either an enable Boolean input or an execute Boolean input. Function blocks with enable inputs are functional as long as the enable input is true. And function blocks with execute input use the rising edge of the input to execute the command. The function blocks will also have some outputs like busy, active, done, error, error ID, etc. These outputs indicate whether the function block is busy or has executed successfully or failed and the reason for the failure. In case of MC power, the status output indicates the operational readiness of the access. Further movement commands will only work once the status bit is true, indicating that the access is fully enabled. The busy output stays true as long as the function block is called with enable equal to true. Active indicates that the command executed successfully. Error output gets set if an error occurs. The cause of the error will be indicated by the error ID double integer. The MC reset function block is used to reset the NC access after a fault. In many cases, this leads to a reset of the connected drive device. The access makes the transition from the state error stop to standstill or disabled by resetting all internal access related errors. The reset command executes on the rising edge of the execute input. The done output becomes true if the reset was successfully executed. Busy stays true to indicate that the function block is not finished and the new output values are to be expected. Once reset has completed, the busy output becomes false and the done output is set, unless an error occurred, in which case the error output is set. The MC set position function block can be used to set the current access position to a desired value without causing any movement. This function block can also be used during motion without changing the commanded position, which is now positioned in the shifted coordinate system. The command is executed on the rising edge of the execute input. Position input is the value that the access position will be set to. In absolute mode, the actual position is set to this value, and in relative mode, it is shifted by this value. If the mode input is false, the access position is set to an absolute value. Otherwise, the access position is changed relative to the specified position value. The done output bit becomes true if the function block executed successfully. The busy output stays true as long as the function block is called with execute bit true. Let's look at our first motion command function block. MC move absolute. This function block commands a controlled motion to a specified absolute position and monitors the axis movement over the entire travel path. If no further actions are pending, the execution ends with velocity 0, which is the standstill state. If you recall the state diagram where a discrete motion ends with standstill state if completed successfully. The function block's done output bit is set once the target position has been reached. Otherwise, the output command aborted, or in case of an error, the output error is set. The access input is used to specify the NC access for the move command. The command executes on the rising edge of the execute input and uses the values for position, velocity, axle, decel, and jerk. If the axle, decel, and jerk values are not specified, then the default settings will be applied. However, if the velocity is not specified, then the zero value is taken, which means that the axis will not move and will result in an error code 17241. This error can be cleared by resetting the execute input to this function block. The MC move relative function block works similarly to the MC move absolute function block, except that instead of specifying an absolute target position, the relative move distance is specified. The axis moves from the current position by the distance specified and then comes to a standstill. And similar to the move absolute function block, the done output bit gets set. Otherwise, the command aborted output, or in case of an error, the output error gets set. For applications where continuous movement, either linear or rotary, is required, we can use the MC move velocity function block. This function block is used to start an endless travel with a specified velocity and direction. The movement can be stopped through the use of a stop command, which we will review next. The motion starts on the rising edge of the execute input and reaches the final velocity specified by the velocity input parameter. The dynamics used to reach the velocity can also be specified by using the axle, decel, and jerk inputs. After the axis acceleration, the in-velocity output becomes true once the requested target velocity has been reached. The in-velocity output remains true until the axis velocity has changed by another command. As soon as the velocity deviation is determined, the output becomes false. Once the axis is set in motion, there are two available function blocks to terminate the motion and bring the axis to standstill. The MC stop function block is used to stop an axis with a defined deceleration ramp and locks the axis against further motion commands. The function block is therefore suitable for stops in special situations in which further axis movements are to be restricted, such as during emergency stop conditions. The axis is unlocked on the falling edge of the execute input. Alternatively, the axis can also be reset using the MC reset function block. For normal movement sequences, the MC halt function block must be used to stop the axis. Unlike the MC stop, this function block does not lock the axis during stopping. The axis can therefore be subjected to another move command at any time during the stopping sequence or after it has stopped. Now that we have covered the basics, I'll hand over to Andrew, who will demonstrate how to use these function blocks in a PLC project to control our simulation axis.
Thank you, Akil. Let's open the TwinCAT project from part 1 of the motion control tutorial. Let's navigate to the axis we created and run it manually one more time from the Online tab. As you can see, I can easily control the axis manually by using the manual control buttons. We are able to do manual control because there is no linking of the axis between the NC and the PLC. Once the axis is linked to the PLC, we will no longer be able to control manually from the Online tab. I'm going to go ahead and create a new PLC project. I'll call it Motion Control PLC. The first thing we need to do is to add the Motion Control TwinCAT library under References. In the dialog box, search for TC2MC2 and select the library from the list and click OK. The Motion Control library is now added to the PLC project. In the main POU, we can now create an instance of the axis by using axis ref. I'll call it My Axis. Next, I am going to add another POU to create the logic for implementing the motion control function blocks for controlling the axis from the PLC. I'll call it Program Motion Control. For the implementation language, I think let's program it in CFC or Continuous Function Chart, and I will rename the program and add the CFC to the program name. Here we will be creating instances of all the function blocks that we will be using. Let's start with MC Power. Next, we need a bit to enable the axis. Now, I will add a box for the MC Power function block. Our function block is ready. Now we can link the inputs. Next step is to go to the NC axis and link it with the PLC axis that we instantiated. Currently, our PLC axis instance is not listed. Let's go ahead and do a build to compile the PLC project. Build succeeded. Good. Let's try linking to PLC again. Our axis is now listed. I'll select it and press OK. It now shows that the NC and PLC axes are linked successfully. The next step is to activate the project. We can see from the green gear icon that the project has been activated successfully. Since the NC axis is now linked to the PLC, manual control of the axis will now be restricted. As you can see, I am not able to enable the axis anymore. Let's go back to the PLC and enable the axis from there. I will use the MC power function block that we instantiated earlier. But first, we have to call the new POU from our main program. Now we can log in with download. Our MC power function block is now active as indicated by the active output status. I'll go ahead and set the enable bit to enable the axis. We can only see one checkmark. The feed enables are not set. Let's see why. We have not linked anything to the feed enables. I'll just the same bit and tie it to all 3 enable inputs. Okay, let's try that again. This time we can see all 3 enables are checked. Our axis has now been successfully enabled from the PLC. Let's disable it by toggling the bit to false. The axis is now disabled. Next, I will add the motion control function blocks like positioning and velocity control, as well as relevant inputs required like input execute bits. All required function blocks have been instantiated in the declaration section. We have to build the solution to compile our variables. The solution has been built without errors, so I'll start adding the programming blocks to use our function blocks now. Adding the execute input next. Next, adding the position, velocity, and acceleration inputs. Alrighty, let's log in and see it in action. I'll set the enable bit. We can see from the NC that the controller is fully enabled. We can also see that the status output of the MC power function block is true, which indicates that the drive is ready for operation. Now we can test the move absolute function block. I will enter some values for the velocity, position, and acceleration inputs. Now, I will set the execute input bit. The function block should start execution on the rising edge of this input. Here goes. And we can see the axis position increasing to my target set point of 30 millimeters. Next, I'll show how to implement the relative move operation using the MC move relative function block. Okay, what I have done is combine the status output of the MC power function block with the execute bits for the move commands. That way the move functions don't execute unless the axis is ready for operation. Okay, let's see it in action now. I'll set the inputs for the move relative function block. I am setting the distance input to 10, so that it moves 10 millimeters relative to current position. Okay, let's set the execute input to start the relative motion. Okay, good. It moved to position of 40. Let's try again. It did another relative move of 10 millimeters and stopped exactly at 50. How great is that? I still have a few more function blocks to show you. I am going to come back with all the additional function blocks implemented and then demo the operation for you. Hang tight. I'll be right back. And here is the full logic with move velocity and set position commands, as well as stop and reset function blocks. Now, in order to make the subsequent demonstrations easier for our viewers, I will be using the visualization from one of our earlier tutorials and modified it slightly for use in this application. This visualization shows the status feedbacks from the NC. In order to use them, we have to do a cyclic call to axis.readStatus, which I will add before calling our motion control program. Okay, we have the visualization and the logic side by side. Let's start by enabling the axis. The axis is enabled. However, we can see that the actual position is currently at 100. Let's use the set position function block to set this to 0 position. Okay, our position has now been reset. Let's try the move operations from the HMI. I'll use the move absolute function block to drive the axis to position 50 millimeters. We can see from the NC motion status indicators that we've accelerated to the set speed and traveling to the target position. Once we've reached the target position, the axis comes to a standstill and the not moving bit is now on. If I trigger the move absolute function block again without changing the target position, it does not move since we're already in position. So instead, let's try the move relative function block with the distance input set to 50, and we can see the axis traveling to the new target position by 50 millimeters. We can repeatedly trigger the move relative function and it will move the axis by the set amount each time. That's great. Next, I will demonstrate the move velocity function block. The logic is programmed to use the same velocity and acceleration inputs for the move velocity function block. We can see that the axis accelerated to 10 millimeters per second and is now in velocity and will keep moving indefinitely until we stop the axis. I have tied the stop button here to the input of MC halt function block. Triggering the stop push button decelerates the axis and brings it to a standstill. Let's try again with a higher speed this time. The axis accelerates using the acceleration input set point. It has now reached the set target velocity as indicated by the end velocity indicator. I will now stop the axis and demonstrate what happens when you trigger a move command as it is stopping. As you can see, the axis immediately starts accelerating as soon as the move velocity function was executed during the stopping phase. Let's run the axis again, and this time, I'll use the MC stop function block instead of MC halt to demonstrate the difference in their execution. As you can see, the axis starts decelerating and stops. At the same time, the axis also gets locked as soon as MC stop is triggered. The axis can be unlocked by removing the execute input to the function block. Alternatively, the axis can also be unlocked by triggering the MC reset function block. Let's try that. So I'll run the axis again and trigger the MC stop function block again. The axis is stopping and gets locked simultaneously. This time, I will use the reset function block to unlock the axis. The axis unlocks even though the execute input to the MC stop function block is active. You can handle turning off this bit in your application logic. For the purposes of this demo, I will just use the HMI button to turn it off manually. Next, I'll be demonstrating the use of MC reset function block to clear axis faults when the axis has faulted. One easy way to fault the axis is to remove the controller enable while a function block is active. Now that the axis has faulted, we will use the MC reset function block to clear the fault condition, which is indicated by the red LED here. With this, you have seen how the function blocks from the TC2MC2 library can be implemented and used in logic. For this tutorial, I chose to program our PLC motion control logic using CFC programming language. However, the same results could be obtained by using any other programming language, be it structured text, ladder diagram, or any other available languages in TwinCAT. Thank you for sticking around and hope you enjoyed this tutorial. If you have any questions about anything that I showed today, then please leave your questions in the comments. If there is anything else you want us to explain from this library, let us know and we will try to incorporate that in a future tutorial. With this, it's goodbye from me and back to Akil.
Thank you for the demo, Andrew. Coming up in part 3 of this tutorial, now that we are able to control a simulation axis programmatically from the PLC, in the next tutorial, we will hook up an actual drive and motor and learn how to integrate them with the back-off system. Specifically, we will link the NC to the PLC and the I/O, and use the same PLC project from today's tutorial to control the real motor. So stay tuned for that. That's all for today's video. Hope you found it helpful. By the end of the motion control tutorials, you'll be easily able to run your VFDs and servo systems from within TwinCAT. In the meantime, if you have any questions, please put them in the comments below. If you'd like me to cover any other motion related topic, please let me know and I'll try to incorporate them in a future tutorial. If you found this video helpful, then please consider subscribing so you don't miss out on future tutorials. As always, thank you for watching and keep innovating.